Now we're going to use water films for a two-dimensional crystallizer, where you grow crystals within the confines of one of these films, but the fluid mechanics and the crystal growth are going to be basically limited to 2 dimensions. That you're not going to have this third dimension involved because you're restricted to this boundary of this thin film. And for the crystal systems that we had available on space station, we had sodium chloride, a salt from our galley, and we had sugar from our galley, and we had some jello from our galley. And so you will see examples of these systems in the process of thin film crystallizers. So let's take a peek at the video. And what you see here, again, one of these 50 millimeter diameter films, about 300 microns thick, and this is made with a saturated sodium chloride solution taken from our galley, and you can see the salt crystals starting to grow in these films. And what we see here is a time-lapse sequence showing these crystals growing over about a period of a day. You can see the crystals are growing, and the crystals actually grow to a point where you can get them up to 10 millimeters on an edge. It's really kind of neat to see these crystals growing, and they're primarily growing in a two-dimensional geometry. They're very thin. They're maybe 500 microns thick and 10 millimeters square.
And that was so cool, we're going to see this a second time. And you can see these crystals are forming. Some of the crystals are hexagonal, and some of the crystals are square in cross-section. Here are crystals close up to ones currently growing in a film. And you can see there are square crystals and there are hexagonal-shaped crystals. Both of those are consistent with a cubic crystal system, depending on which orientation the seed started to grow. And you can see diagonal lines in the square-shaped crystals, and these lines are not voids, but they're actually filled with sodium chloride that is very transparent. And this is a demonstration to show how mobile these crystals are within the film. If you puff on them just a little bit using a syringe with a cannula, you can see that you can move these crystals all around. Now here's a demonstration to show that the crystals seem to congregate around the edge. When I puff on them and force them away from the edge, they go right back to the edge. And this is due to some really interesting surface tension forces involved. The side of the film is slightly curved due to its attachment to the wire, and the crystals distort the surface of the film. And here you can see a reflection from the surface of the film, and you can see how the crystals are distorting the surface of the film. And the combination of the distortion of the film surface by the crystal and the curvature of the film as it approaches the wire makes forces that cause the crystals to go next to the wire.
And here's another time-lapse sequence showing the sodium chloride crystals growing. And what's interesting is to see little spots on the side of the wire that nucleate crystals. They nucleate seeds. And so you'll see a little seed crystal forming on the edge of the wire, and it'll grow to a certain size and get spit off, and then another crystal will form in its place, and it'll get spit off. And you can see this process happen over and over again at these hot spots on the sides of the wire. And then you can also see crystals spontaneously form in the center of the film and continue to grow there as well. And then you can take these films all the way to dryness, and here we see a mass of crystals just suspended in these films after all of the water has evaporated.
And here is a crust left over, it's completely evaporated, of a microcrystalline film, and this formed from a crystallizer where I reached in with a pair of metallic tweezers to remove a few seed crystals, and within minutes, the whole crystallizer crusted over with this polycrystalline mass, and then after it dried out is what you see. And here's a time lapse of a film that I touched with the metallic tweezers, and you'll see it crystallize into one of these masses and dry out. It almost looks like the movies where someone gets turned into a pillar of salt. And here's this microcrystalline sodium chloride film after it's dried out. And what I thought, if you want to harvest crystals without making that microcrystalline film grow and take over your crystallizer, the best way to do it is to reach in with these Teflon cannulas. And here I have two of the cannulas, and I'm pulling crystals out, sort of like operating with chopsticks. And you can pick and choose. You see a good seed crystal that you want to pull out, you just go ahead and pull him out and leave the rest, and then you can start a second crystallizer film and plant that seed crystal in and have that seed crystal grow to a much larger size. And all of this is just standard crystallization technique that you can do on the ground or in space. But the uniqueness here is that we have this two-dimensional thin film, and we're growing crystals in the absence of the kinetics that typically occurs in 3 dimensions. And these crystals do have some finite thickness, so they're not a two-dimensional body. They do build up some thickness, thick enough so you can pick them out. But the dynamics associated with them growing is more on the 2D level than the 3D level.
Now here we see a different kind of film being made. This is a protein film. And this particular protein, I believe, is a blueberry-flavored protein. And it could also be called Jello or gelatin, but it happened to be the only readily available protein solution I had. And we drew these films, these protein films, on the wire frames, and they would solidify into something that would be like a plastic wrap, plastic food wrap. And so now the question is, what can you do with one of these protein films? And what we decided to do was to use it as a means of suspending small chemically reacting droplets. And so here you see 4 water droplets suspended in one of these protein films, where now you can have carefully controlled diffusion going on between the constituents in the aqueous droplet and the constituents in the film. And the first example of what I could think of doing with these films was suspending spherical droplets of sodium chloride solution, just to show that you can have an exchange of between the protein film and the sodium chloride, and you end up with these 3-dimensional crystallizers. And here's a little time-lapse sequence showing the sodium chloride crystals growing. And here they've been taken completely to dryness, and you can see that we indeed have 3-dimensional crystals that have been grown in these films. And here's an example of showing the integrity of these protein films, where you can take a pair of scissors and you can cut the film out from the wire frame, and you're left with a protein film that has a fair amount of integrity with the sodium chloride crystals embedded in the protein film. And again, this is not so much to show that we want to make films of Jello with sodium chloride on them in the weightless environment, but just to plant seeds in people's minds, showing how we might possibly use these films in a weightless environment for growing crystal systems, protein systems, possibly chemical reaction control between droplets suspended in the protein films, how we might be able to use these for other scientific investigations where you have resources available to you that just don't come from the galley area. And here's a film crystallizer showing sugar crystals growing over a period of about a week. And they grow in stages where you get these needle-like crystals growing out from centers, and they slowly take over the film. And the end result is what you see here, where the whole film has been solidified, crystallized into this polycrystalline mass.